Anyone else need homework 1 who hasn't gotten it? Here, roughly alphabetical by last name. You need to turn in homework 2. It's here. You can do it at the end of class 2. Lecture tutorials here.
Are those graded?
Lecture tutorials are not graded. Lecture tutorials are just ways for you to work through it on your own. Ideally with another person. Not more than 3 people, but more than yourself. Yeah. Dude, I don't even put it in my office. I literally send it to my office manager. Yeah.
Yeah, the library upstairs has a huge building. No, I don't put it in the library.
Okay, let's get started. Oh, wait. Don't give them back. No. Sorry, don't give them back. Turn them in there. Sorry. No. My bad. They won't be graded. My apologies. Okay, so how did homework 1 feel? Pretty good? Are there people, like, now that you've had time to think about it, everyone's mostly turned it in? Are there questions that folks had they want answered? No. Okay. Some common themes I saw. One thing that I would love in your answers is to hear from you. So short answers are not as fun as long ones. So when I ask you, what are the most important aspects of your final grade? It's perfectly fine to copy and paste the syllabus because that's accurate. But what does it mean to you? Right? Interpret it. Right? So I'll just ask for more sometimes. Everyone had great examples of non-scientific questions. Those were really fun to see. You'll see this type of question a lot where you have to correct a friend who's kind of right. Okay, that's like a skill that I want you to be able to walk away with. Is to like how to hear part of an argument that's right and still be able to jump in. One of the main things that I pointed out in this third one, and I think a lot of folks are getting it, is let me know ahead of time. You know, let's say there's an apocalypse and you can't come in because the sky is red. Just let me know, right? We can live with the fact that it's 5 days late. No one really cares, right? As long as the work gets done. But if I don't see that you're contacting me and you turn in all the work late, what happens? Not accepted. Correct. Good. All right. We're going to play with ChatGPT, but maybe not on every homework. So homework 3 is out and it doesn't have a ChatGPT question, but maybe you've been using it to like have a nice conversation with the computer. That's perfectly fine. I don't mind, you know. Okay. And then the last one, I think most folks had a real hard time with it before I posted the video. And then everyone was like, oh, okay. So it's just a computer, right? I just want you to be able to think about how we contextualize some of the numbers. It's not a math class. I really want you to think about what does this number feel like? Now, for some people, they put really unique objects to compare to, like 16 feet things that you might not think of. And some of them were just wrong. Like a 16-foot, I don't know, a chair is not 16 feet or, you know, something similar, right? So you really want to make sure that it's not just the random answer. Okay? Cool. Comments, questions, concerns on this one? And if you have individual questions about your feedback, or if you don't like it, let me know and we can talk about it. Yeah. Cool. Anyone notice how it's much cooler today than it was like a week ago? Yeah. Does anyone notice that that's correlated with the smoke that you're feeling or seeing? So this is like a little like teaser for how the dinosaurs died. It's like a little, little trailer. So, at the end of last class, we talked about Newton's laws of motion, and I showed you this rocket. And I realized that most people were like falling asleep, and I was like, all right, let's not do that. So I was gonna go into a different topic, but now we're just gonna sort of jump a week ahead into planetary processes. And like this is a class about seeing cool things on planets, so let's do that. I'm going to show you cool things, and we're going to try and build a mental model for how planets look. Why do they look that way? And we will come back to those slides a little bit later. That's great. We'll come back to those slides later, but we'll do them right in the context of how the solar system forms. So, for example, in order to understand how stuff moves in space, you should probably then talk about stuff moving in space. But I didn't want to do that until later, so I just dropped it. So if, for example, you look at homework 3 and you say, man, there's no discussion of gravity in there, that's okay. We're not going to really talk about gravity except for in the sense that like I'm flowed down towards the Earth. That's all you need to know currently. Is that okay? All right. We're going to look at cool pictures. Today is cool picture, and so is cool picture for like the next 4 weeks. So if you like cool pictures, I got you. Got you right through census, and then you can't drop. That's good. Good job. What are we looking at? Good. Volcano. Why this volcano? Yeah, there's lightning in it. That is not fake. That's a real picture with real lightning in it. It's pretty rad. This happens very rarely. This is one of the major geologic processes that we're going to talk about in the upcoming couple weeks. This is a process that shapes the surfaces that we can stand on. You also see stars in the background. That's 2 photos. So this one with the lightning is taken first, and then you take a long exposure with the stars afterwards. Okay. So we're going to talk about planetary geology. We'll ask the question, why do the planets look so different? We'll throw in the moon as well. I know it's not a planet. Don't get mad at me. It's just words. We'll ask the question, why does the Earth have life, but no other planet that we know of? And are there just processes that occur on all planets? Are there anything that we can see like ties together these bodies, or is it just random? Right? That's the major questions we want to ask today. Here are your terrestrial bodies. Terrestrial just means of the Earth, like similar to the Earth. Now we'll see that they're very different from the Earth. But what I mean by that is you can stand on them. Okay? There'll be some planets that we talk about later. You won't be able to stand on them. You just fall apart. Okay? This one you know, hopefully. What about it is good? Okay, we live in it. Yeah, that's a good one. What else about it? Habitable. Okay, we live with it. Yeah, that's good. But what about it? Ocean, standing on it. Okay, those are both very good. I like both those together. Ocean's great. You need to drink ocean. And standing on it, good. Right?
Oxygen.
Oxygen. Yeah, I can't quite see oxygen in here, but like I know it's there. So that's good. We're going to use a lot of our eyes today and try to see the things. Because we have spacecraft data. Objects go to these planets, they take photos, and we construct models from them. Okay, let's look at our neighbors. Less fun looking. These two, they look kind of similar, right? Is that the same photo twice? No. It's kind of wild. That one on the left is Mercury. That one there is the moon. We've been there. We haven't been there. I mean, I have, like, as humans. Okay, this one, that's fun, right? Venus. Is that what the surface, or is that what Venus looks like from space? No. All right, someone knows, read ahead. So this actually is when you remove the atmosphere. It looks like that. That's what the surface looks like. And we'll talk about the atmosphere in the atmosphere section of the class. This one, best one after Earth. It has ancient riverbeds. So you can see here on the Earth, right? This is the ocean. Figure that out. These are mountains. And water will carve paths down through. Right? Water will be deposited in the mountains, run downhill, and carve channels. The same thing happened on Mars. They carved these rivers. And now the water's. So that's a big question that we want to answer, right? How is it that something could look very similar to what the old Earth looked like? And then, of course, there's a hidden question on the bottom of that. Did Mars ever have life? Right? Okay. We're going to make some comparisons really quickly. Mercury and the moon, we're going to sort of lump them together. They're very heavily cratered. So we'll talk about what that process is, what causes those pock marks, right? So these things that you see all over the surface, these are not volcanoes for the most part. Right? They're craters. Why doesn't the Earth have any? Perfectly good question. Mars seems to have less of them, and Venus in this tiny picture doesn't appear to have any, right? There's going to be some volcanic plains on Mercury and the moon, but no volcanoes, generally speaking. Venus has lots of volcanoes. Big volcano, very few craters. Weird bulges on Venus. We'll talk about that. Mars, we talked about dry riverbeds, maybe had ancient running water. We think almost certainly. The largest question is for how long? Was it quick bursts of water, or was it sustained periods of rivers? And similarly, was there ever an ocean on Mars? And then the Earth has almost everything else. Plus we got water. It's great. Best planet. 9 out of 10 stars like that. Okay. Okay, no one else has a better one. All right, I'm going to show you 4 bodies. Now that you're all experts in planetary geology, which one's which? Raise your hand. Raise your hand if you have any answer. For any of them. You can get the easy ones first. Yeah.
Bottom right is Mars.
Wait. Just one at a time. Just one at a time. Bottom right is Mars. This one? Okay. Yeah. Top right's Earth. Top right's Earth. Okay. In the back, hold on.
Top left, the moon.
Top left looks like the moon. Okay.
Bottom left is Mercury.
Mercury. Okay. Okay. So these are some of these are in color. Some of them are not. I made them all black and white, otherwise it gives it away. What's the giveaway for this one?
Rock formation.
What do you mean by rock formations? They're all types of rock, right? For example.
Canyons, close, like you can see more detail. So
See more detail, right? So it looks like the picture was taken a lot closer than this one, right? Like I took this one, right? So it was taken one from the surface and much closer to this object than this one, which was taken from the surface. Okay, so we're almost completely right there. Come on now. That's the true color of all of them. So that's Bryce Canyon in Utah. That is Mars, but this one is not. This is Venus. You can tell that from that weird color that we had before earlier. What's this one? Why is this one from the angle that looks like you're standing on it? The moon. It's from when we were landing. Pretty cool. And that's the real color, which is pretty wild. Like no color anywhere. I mean, there is color, obviously, but it looks black and white until you're standing on it with a white suit. You're going to see a lot of different features here. So this process, this perfect little hole is called an impact crater. This is basically when you smash into the surface, has energy equivalent to like a nuclear warhead. And so it blows out all the Earth. And that's not Earth, sorry, that's moon, but you know what I mean by that. Okay. This process here is called erosion. This is where you start with rock and you let wind or water slowly degrade it and turn it into something that looks really cool, really beautiful, but it's no longer the rock that it once was. So this used to be like seafloor, like layered seafloor deposits, and then water cut through it. So for example, if you've ever been to the Grand Canyon, what's at the bottom of the Grand Canyon? A river. And the river's been running for millions of years. Not millions, yeah, probably millions. cutting through, right? That rock. Good. So water turns out stronger than rock. And no, like that. This one here, pretty cool because you have two different tectonic or different geologic features. What is this thing? A mountain, good. Find a mountain. No, not quite. Good guess though.
The volcano.
A volcano. Yeah. So this is a volcano, and interestingly enough, so this that's the place where the magma, the lava comes out, right? And then it flows down, right? And then at some point, there's probably some water or something that collected in the top here, and then it all melted and it carved a channel through that and formed a little lake at the bottom. Okay. So we'll talk about these types of volcanoes. We'll start with volcanism today. And this stuff here, these like ridges and wrinkles, these are tectonics. So we may be all familiar with plate tectonics. This morning, there's a fun little earthquake in Malibu, right? A 5 or something like that. And if you've ever gone hiking in the hills behind here, you get the San Andreas Fault, right? So it's pretty cool. You can go walk and you can go see it. And that's the place where two plates are doing this, sliding past one another. Yeah. This is a different type of tectonics. And we'll talk about that when we talk about Venus in detail. But any time that your crust is moving or crumpling or deforming, we call that tectonics. So here's the words. Volcanism, volcano. Impact cratering, smash into the surface, boom. Tectonics, ground moves. Erosion, wind and water are king. Okay. Questions about these processes? Okay. Yeah, most of these photos are from here. This one is not. That's from the moon. That's a volcano on Earth. You can tell because it's taken from the edge, it's getting to the surface. This one is taken in Colorado. Beautiful sandstone there. And this is the Grand Canyon, as previously mentioned. Yeah.
Any major impact like craters?
Yes, and you can go to one. I'll show you that when we get to impact cratering. Yeah. Just giving it away. You don't want people to know where it is. Then they'll go visit it and have a great time. Okay, all right, good. Okay, so let's talk first about volcanism. Let's define it and then let's look at some different types. So basically, it's stuff on the inside getting to the outside. Stuff inside hot. When it makes it to the surface, it cools down and it hardens. Okay. So any molten rock making it to the surface is volcanism in this broad definition. Okay. Let's look at some different examples. The interior of the planet is very warm, hot enough to melt rock. And it's also under a lot of pressure. So as the rest of the planet swishes down in it, it's both hot and it's got a lot of pressure, which keeps that rock, which you would think of typically in your mind as a solid, it turns it into a liquid, right? And this isn't like a liquid, like a cup that you would drink, right? This is like a molten fluid, like you can see coming out of any volcano. See this? So this is a volcano and there's a river of rock. Now, if you give it long enough, it'll cool down and it'll just become rock, right? But in the interior of the planet, it's molten. Does that make sense? Okay. Fine? Yeah. All right. There's 3 different types of volcanism, and it's distinguished between how runny it is. So what I mean by runniness is that I don't even have my water today. Okay, water, you like pour it, easy, comes out really quickly. Honey, not like me calling you like honey, like the stuff. You like pour it, and it takes a while. Good, right? That's a measure of something called the viscosity, the resistance to flow. Okay, so what I mean by that is you have some stuff that's very runny, similar to water, and that forms lava plains. So we'll see some pictures of this. As it comes out of the earth, very runny, and it just flattens out almost immediately. And then you have some stuff that has a little bit more goopiness. So rather than just flatten out immediately, it builds volcanoes, but they're very wide and they're not very tall. And then there's stuff that's super goopy and it creates really tall volcanoes. So that's the major issue here, right? How tall is your volcano? How goopy your magma is. Cool. And of course, the thing that everyone knows it for is that volcanoes erupt. Right? That's the cool part about them, maybe the scary part about them. And that happens because the interior of the planet not only has rock in it, but it has gases that were trapped inside those rocks when they were put into the surface. And they've been held at pressure for a long time. By the time they make it to the surface, it's like water in your when it's boiling, moves from the bottom and then the bubble pops. It's that process of popping that releases the gas from inside of a liquid. Make sense? Okay. If you have a lot of gases inside of that rock, it makes it very explosive. So we'll see an example of steep-sided volcanoes with a lot of gases. When they do erupt, they're very violent. As opposed to if they're more shallow, then the gases can get out very easily. They're not stuck in the molten rock. And so you kind of have more gradual flows. Okay, so this is the diagram up here. There's like, I don't know if everyone can read that, but there's just like magma in different pockets. And where there's, weak points in the crust, stuff comes through. Pretty straightforward, right? Okay. This is a great example. This is in Iceland. Iceland, very volcanic. Anyone been to Iceland? Anyone seen photos of Iceland? Okay, photos of Iceland. So they have a lot of black sand beaches. That's all volcanic rock. And you'll see some of this over and over, that the types of rocks in here are very dark when they come from the inside of the earth. Okay. This is an example of gas and a dust being ejected from a volcano in Iceland. So here's the cartoon picture. It's a little more complicated than this, but for the purposes of this class, this is as far as you have to go. Okay. The complicated physics thing here. Hot stuff rises. Okay. Cold stuff sinks. So here you have something in the middle. We're not going to talk about why. In the middle, it heats up the magma. Then the magma rises when it's hot, makes it to the surface, cools down, and sinks. Okay. Cool. Okay. Let's look at some runny lava. So this is an example on the moon of these lava plains. They're called lunar maria. And they're basically giant basins where very runny lava seeped through the surface. And because it was so runny, it doesn't have any like texture to it. It doesn't have like mountains, just flattened out like an ocean and then cooled. And so it's very flat, just like the surface of a lake might be, right? And you can see that on the moon. These are the dark spots on the moon. So here you have all this white stuff. These are called the highlands. We'll talk about that later. And then each one of these is a basin where lava, very runny lava, just filled it in. And then it cooled and it would start. Cool, right? Okay. And then, of course, this is what happens when the lava is not so runny. Come on now. You get shield volcanoes. And shield volcanoes are abundant in the solar system. So I'm going to show you a couple different types, and then we'll compare them to Earth's. So this is a picture of Sapis Mons. Mons just means mountain or mound. And this is on Venus. So what you can see here, not a very good photo. And I'll explain why that is. But you can see there's like, it's like a mountain, but there's a hole in the top, right? And in addition to this, there's some like really bright reflective material coming down, right? So you might be thinking with your head, you're like, oh, I've seen mountaintops that look like that. That must be snow, right? No, no, this is lava. So this is really bright lava. You're like, well, Dr. Guzman, you just said that lava was dark. What's going on here? This is not a visible image. This is an image taken with radar. So as we see the planet Venus later on, when we talk about the atmosphere, you can't see to the surface. It's got a very thick atmosphere. And the only thing that can penetrate all the way down to the surface is radar. Now, what I mean by radar is the same thing that you use to, like, find ships, the little thing that goes bing, bing, right? Not the one that's in the submarine, that's sonar, but the one where you're in the boat. It's like another boat is nearby, you gotta shoot it, okay? So that's radar, okay? We can use that to ping the surface. We bounce a radar beam at the ground and it bounces back. And it tells us what the composition, what it looks like, right? Okay, so this stuff up here is really smooth, like lava flows would be, right? Because it was liquid recently. Okay, and this stuff down here is all textured and broken like rocks are. And this one over here, another volcano. I'll show you a map of the volcanoes and the craters on Venus. And this is by far one of the largest volcanic objects in the solar system. Let's see why. Okay, so there's Venus. Come on now. Anyone know what this is? Hawaii. Yeah, okay, good. You can read. So this is a shield volcano called Hawaii. It's awesome. So basically what's happening is there's just a little hot spot, a little place in the crust where it's a little thinner, and the crust is moving along it. And it's just poking through and just creating islands. So this will be the new island of Hawaii. You can go online and like look for photos and video. On YouTube, it shows like you can take a little boat and you can see that it's finally poking its head through the water as it like spews out magma to build a mountain in the middle of the ocean. This is, of course, that's the big one. And they still have eruptions too. But as you go farther and farther back, these were all formed from that process and they slowly degrade due to erosion until they're underwater again. And they're reclaimed by the sea. Okay. These are shield volcanoes. So when we see a video of them, we expect the lava to run, move very easily. And I'll show you an example of that, I think, in a few seconds. And then you have more on Mars. And there's your Olympus Mons. Right? This is the largest solar system. This is the largest volcano in the solar system by a lot. Mars is not the biggest planet of the many that we're seeing. So Mars has two cool things. It has the largest canyon system and it has the largest volcano. And we'll talk about why that is. This whole region, you can see huge, huge volcanoes, right? This thing's massive. I'll show you in a few seconds how massive. And then it has these friends. This whole region was very volcanically active for a while, and then it all shut off. So right now they're completely dormant. Okay. This is another example of Venus. And now I'm showing you that same object from before, but I'm overlaying on it some data that basically tells you how hot it is. Right? So you can ask the question, is it erupting now? And the answer is yes, it's very hot. Right? Lava is coming out of this object currently. So you're not just looking at dormant volcanoes on Venus, you're looking at erupting volcanoes. Okay. Let me show you how big these are. Okay, here's our favorite one, right? Mount Everest, like big climb. Big climb. That's Olympus Mons on Mars. So that's like 1, 2, a little bit more than 3 times. Yeah, it's pretty tall. Okay, this thing is so big, Olympus Mons is so large that it sticks out basically into the atmosphere. Here you have to use like oxygen if you want to survive. Up here you would have not a good time. The pressure would be so low. Okay, this is like where planes fly. 22 kilometers is like how high planes are flying, right? Olympus Mons is really cool too. I'm going to show you how wide it is in a few seconds. if you were to stand on the top of it, you look around in all directions and it would look flat. Okay, let's let that process for a second. So you stand on top of a mountain, it's like this, you stand on top and you look down. This is so wide, it's obviously very tall, but it's so wide that you stand on top and it looks flat. Okay, so let me show you how big. There's Arizona. That's Olympus Mons. That's one volcano on Mars. So you stand here, right? I mean, I don't know how many people have visited Arizona, but you can't see the edge of the state. And the coolest part about this too is that, I mean, it's just very convenient, it fits into it. There's like basically a cliff right at the edge. So as this volcano spewed lava, it would just run down the sides until it stopped and cooled. Very runny lava, not very goopy at all. Right? So these are examples of shield volcanoes. And we call them that because they form like big circular discs, sheets. Okay. Yeah.
Or like, was it kind of smooth?
Smooth, yeah. I mean, like, we don't have high enough resolution to like know like whether or not it would be grainy in the same way, like if you go to like the ground up there is like chalky and there's like individual rocks, but certainly from space, this is much smoother, for example, than nearby areas, which have a lot more texture or more mountainous, etc. Right? So this is probably more similar to if you did go to Hawaii and you walk on any of the fields there, the lava fields, they're very small, like grains. And so it looks very smooth, right?
Is there a reason that it was so large a volcano, so very, very active volcano?
Yeah. So it was active for a very long time. On Earth, we have sort of volcanoes that sort of pop up and they go away, become dormant and they go away. On Mars, essentially what happened is, like I said, hot stuff go up, right? So whatever was heating the interior of Mars, which we won't get into, rather than distribute the heat in all of these different directions, it formed what was called a superplume. And it just was like a fountain of heat just pointing at this region for a really long time. And so that's why this region in particular, very volcanically active, and also a lot volcanically active compared to nearby regions, right? Is that helpful?
You know why it's more like a brownish color compared to the grayish, like outside?
Oh, I don't actually know if these are true colors. This might be, this might have like contouring put in to like show the altitude. Good question. I'll find out. Okay, so let's also now ask questions about outgassing. So again, these are Earth. You can tell because of the blue. That's very helpful. Atmosphere that we like to breathe. And the interior has these gases inside of the planet. And one way for them to get out is through volcanoes. So when we talk about, in a little while, we'll talk about the carbon cycle, what it means to put stuff back into the planet. So this is the other half of it. How does it get out? It's through volcanism. How is the atmosphere delivered and replenished? Through this. And so if, for example, you were very small and you ran out of volcanoes, you had no way to replenish your atmosphere, you might lose. That's highlighting something else later. Okay, this process makes sense? Questions, comments, concerns? Okay, let's talk about impact cratering. Okay, so we were talking about Galileo, and he was using his telescope. He's looking up at the moon. And he's like, man, there's like mountains on it. There's like these holes. And he didn't quite understand what they were. Right? And they always look really circular. Has anyone ever been at the beach and they're skipping rocks? Everyone skipped rocks. And then you like shank one and it goes right into the ground. Does it leave a circle or does it leave like a long strip? Like, how do you make a hole in the dirt that's perfectly circular? Yeah, you have to drop it like straight down, right? You can't hit it from the side, otherwise, and you can do this at home, right? So water the ground and throw a rock in it. And as you do that, you'll see that it creates a big stripe like that. So people were very confused because they looked at the moon and they saw all of these circles all over it. Perfect circles. And they were like, well, that couldn't possibly be from something smashing into the surface. They got to be like volcanoes or something, right? Like perfect volcanoes for some reason. They didn't quite understand it. And there were some impact craters on the Earth. We'll show a couple examples of those, but they're rare. And they weren't necessarily available to Galileo. They're just like, oh, weird thing that it exists on the moon. Cool. Okay. We know now that they are formed by asteroids or comets. Asteroids are basically giant rocks. Comets are giant snowy rocks smashing into the surface. Okay. We discovered that these were created by asteroids and comets, or realized that they were created by asteroids and comets because of the first use of the atomic bomb. So basically before that time period, people were like, well, there's no way that you can create a perfectly round hole. Then they set off one A-bomb and like, oh, that's a perfectly round hole. So if you have enough energy, then when you detonate, it just doesn't care about which direction it came in. It burrows underground and explodes like a bunch of A-bombs. Okay, or nuclear weapons. Okay, so let's look at this. So this is fun. I'm hoping this works. Let's see if this. Oh, let's go. Hole. Let's try this. Please work, clicker thing. Is the base working? Anyone tell?
Why me?
Okay. Yours is good? Hold on. I don't understand. Why does this thing hate me? Okay, I'm not gonna spend more time on it. If you turn in homework, you get credit for attending today. Sorry about that. I don't know why this thing hates me. Let's answer this question really quickly. How many of the above objects have impact features that can be identified today? The options are Moon, Mercury, Mars, Venus, and Earth. And the answers are 1 through 5. Let me know when you're ready to vote. How many of these objects here have impact craters that we can identify today? Okay, let's vote on 3, 2, 1. Okay, all right, lots of 4s, 3s, 5s. Okay. No one like 1 or 2? Why not 1? Raise your hand. Yeah, in the back.
We already know that. So two of them have impact craters, so that
Which 2?
Mars does.
Okay,
The moon also has impact craters.
good. All right, so minimum 2, right? All right, now there's some ambiguity. So I saw a lot between 3 and 5. So who likes 3? Raise your hand. If you want to explain why you like 3.
I mean, how like he said earlier, this was we know the moon and the earth. Like,
Oh, the moon and the Earth.
I mean,
Okay, so that adds a third one. So you said Mars and the moon, right? So you're adding the Earth. Okay,
Yeah.
good. What about these 2? Anyone want to throw in another one? Yeah.
as well.
We know Mercury does for sure. Okay. So the major question, I guess, here is, does Venus? Yeah. Oh, okay. Okay. All right. Good. Good. All right. We'll see a map of that in a little bit. So let's talk about this process. It's all five. All five of them have craters. Some of them more than other. That's a stupid computer. Oh, okay. So impact cratering probably happened very soon after the solar system formed. And it's an ancient process. So it's not something that we have to worry too much today about. Of course, we still don't want to be hit. Very recently, dinosaurs had a bad experience with that. But generally speaking, when you look at the moon, it's very heavily cratered. There's holes all over it, like it's Swiss cheese, right? And almost all of those happened right after it, right? But the reason that they happen is because stuff smashes into it. And there isn't a replenishing supply of stuff. So after you smash into it, you run out of stuff, right? So likely at the very beginning of the solar system's formation, there was a lot of debris left over from building the planets. And so then you would have it smash into the planets and leave the remnants there. Okay? We'll notice some things like in this image up here. You'll notice that small craters outnumber the big craters. Okay? So you have like one big boy up here and lots of little tiny ones. Right? What does that tell you about the things that hit them? Yeah.
I can tell you something else. I could tell you that I probably noticed that the atmosphere was much thinner.
Sure, right, yeah. So the small ones, the fact that they survived, right, means they didn't burn up. Good. What does it tell you? Oh, it's okay. Go ahead.
Stuff might have fallen off or bounced off of the water turbulence.
Could happen too, right? So sometimes we'll see them clustered together, like these three. They look like they happened in a line. Smack, smack, smack. So maybe the thing that was coming in broke up and smashed into it. What about the relative sizes of the things that hit it? Are there more big things or more small things? More small things, right? Because we can see there's more small craters, right? So, and we'll see this as well when we look at the objects that exist in the solar system. There's only a few big things. Even when you look at the planets, right? It's like one big planet, Jupiter, and everything else is smaller. When we look at the asteroid belt, there will be one big thing there, and everything else will be smaller. Okay? And we'll see this pattern over and over because it's deeply connected to how these objects form. And they're pulled together, they form into a massive body, and then you get smaller and smaller things as you run out of material to build. Right? Like you have one friend, you're all playing Legos, you start with the same amount of Legos, and he starts, grabbing them, and then you don't have as much, and you're just, trying to build a car with what you have left, but it doesn't have two wheels, like, it's missing. Okay? The process makes sense? Maybe not even an analogy. I don't know. We'll try it. Okay, so here's what it looks like. They are hitting the Earth, or they're hitting the body at orbital speeds. So what I mean by that is that they're moving very fast. They're moving at about 70,000 miles an hour. That's about 30 kilometers per second. I know we don't use freedom units, so this is fast. And so the first thing that happens, let's say you have a little rock, it's going to punch right into the crust, right into the ground. And it's going to start slowing down, but it's going to press all of its energy. It's going to deposit that in. And then the crust is going to press back. Remember how we talked about equal and opposite reactions? If I press down on a thing, it presses back up on me. If I wanted to break through my folder, right? You'd have to hold on to it pretty tightly, but I could do it. So here, you press down until you can't press anymore, and then it pops back up. You ever dropped a rock into water? You notice that it rebounds with like a little bit of water that comes back up.
So you're chopping me?
Kind of, but more explosive, right? So you'll notice here, right? It excavates a hole, and in the middle, it doesn't necessarily always pop stuff up in the middle, but it like pushes it out to the side. So the thing started quite small, but it made quite a big hole because it's pushing it all out away from the center. And as it does that, it pushes that material that is maybe buried deep down, pushes out onto the surface so it can be seen. So in fact, we're looking down into the crust, into the surface, right? Okay. Kinetic energy is just energy coming from the fact that it's moving. And so if you're moving faster, you have more energy. So people always say that it's more dangerous to get in a car accident at 80 miles an hour than 60 miles an hour. And that's true. So, you know, you might save 5 minutes, but you might hurt someone way worse, right? In this process, as you come to rest really quickly, you provide a lot of heat. You melt that rock in a lot of cases, and you excavate it. So that means you take it from where it was and you pull it out. So when we talk about the dinosaurs at the end of, hopefully we'll get there, the end of today's lecture, you'll see how this can be a devastating effect. It's very big because you can drop that material onto the planet. So craters are typically about 10 times wider than the object that made them. So you start with something really small and you end up with something about 10 times as wide. Okay. So you've maybe seen one person seen this one. Has anyone else been here? 1, 2. So this is on Earth. You can drive it. You can't walk down. I've been recently corrected. No longer let you walk down. Maybe never did. Somehow I had that in my mind that I walked down there. Never happened. Good thing it didn't hit this building, right? Okay, sorry, I have to do that. It's legal. This is about 1 kilometer across. So you can like drive in. This is like how you get there. You drive in the visitor center, and then you can like stand right here and you can peer into the telescope and then look down here. It's called Meteor Crater, but I want to tell you the quick story about Barringer. This thing is, by the way, it's new. It's only about 50,000 years old. I mean, yeah, that's new for geological scales. So you can already see some processes that we've been talking about. So you see that it punched through the crust, see the layers. So it like went all the way through. You can see some erosional processes because there is water on Earth. So it's the process of grinding that down. If you wait long enough, this thing will completely erode and the walls will just become like will just look like it's deformed, right? It won't look like it has that crisp wall edge. Okay, so the fun thing about Barringer, he understood that like stuff came from outer space and punched a hole in the ground. And this is before the understanding of sort of like how much energy was involved. So he thought, okay, here's what I'm going to do. I'm pretty sure what punched into this thing is like iron and nickel. So rather than going and like mining, you know, somewhere for iron and nickel, which are very expensive commodities, I'll just buy up all this land and I'll find the thing that hit it. Just go and I'll just dig it up. So he spent a fortune trying to basically find this giant object that must have created this giant hole made of iron and nickel, because he found small fragments of it everywhere, like fragments of these meteorite that was iron and nickel. And he never found it. Lost all of his money trying to do this. And later they discovered, of course, that in the impact, there's so much energy that this thing melted completely. So he never had a chance to go mining for this asteroid, which probably was iron nickel, but never mind. This is what it looks like from the side. That's a picture that I took. So it's cool. And like you can like, here's the edge, right? Punch a hole into the desert and you can see the layers. And then of course these slope edges is where stuff is like falling down. You can go visit it. Okay, here's a bigger one. That's 85 kilometers. So let's just go back. How much did I say this last one was? 1. Oh, wow, that's big. That's 85 times bigger. Quick math. Okay, so this one is one of the most prominent ones that you see on the moon. So if you've seen like the face in the moon, the man on the moon, whatever you want to call it, this is the bottom part, right? This is the very bright top section. And you'll even notice, you see these things that look like like tendrils coming off of it. That's that material that was excavated. It's called the eject array. So essentially what happens is you smash into the planet and you take that stuff and you throw it onto the surface really far away. Okay? This is Tycho crater. Oops, there you go. So that's to scale. That's meteor crater, the image that I just showed. Yeah, you gotta squint, right? And then if yeah.
Granted, the source that I heard from this is our podcast, but this is like the depth. Are they all like similar? Is it the same? Like of each crater?
They have what's called the same depth to diameter ratio. So what that means essentially is if your object's smaller, then you make sort of a big hole, right? Wide like this, but not as deep. And if it's bigger, then you make a bigger hole and a similar ratio of depth, right? Okay, so this thing's big. Very big. You can see it from space, right? You can see it with your eye once you know it's there. And I encourage you to go look tonight. So the moon is in a half phase, it's illuminated from the right-hand side, and Tycho's on the available phase. You can see it in the bottom right-hand corner. So this is like the illuminated half tonight. So look in the bottom right. Okay. Okay, one more thing. Here's another one. This is in Canada. I don't know how to pronounce that, so I'm not going to try. This is from a plane. And you can see this like giant ring. That is like the old crater. This thing is only 214 million years old. And you can already see that, you know, one of the major problems with preserving any sort of crater on the Earth is that we've got lots of water, got lots of like stuff that's just carving through it, right? And is eventually going to distort it. Okay. Okay. So now I've shown you this thing where you punch into the Earth and you're all worried, right? Like, is that going to be us, right? Okay, so this is the current impactor rate. And for example, if we think about how big the thing was, right? The crater you have to multiply by 10. So let's think about meteor crater for a second. If it's 1 kilometer, how big was the object? Meteor crater is 1 kilometer. The object was less than that, good, by about a factor 10. So I'd have to divide 1 kilometer by 10, that gives me 100 meters. And no one knows how big 100 meters is, but that's about a football field. So imagine you're Behringer, and you're like, oh, damn, I can find a football field that's just one giant piece of iron nickel. I'll be rich. And so you bought it all. It was completely wrong, okay? So let's look at that. Let's think, okay, 100 meters right here, right? That's the object that Behringer was looking for. How frequently does it happen? Well, about once every, like between 1,000 and 1,000,000 years. It's about like 500,000 years. How old was Behringer's crater? Does anyone remember? 50,000. Oh, perfect. Okay. Good estimate, right? About how right you need to be in this class. Okay. So it's somewhere in between there. And like, you know, that's not good. You don't like any of those words in that order. Tsunamis, widespread devastation, climate change, right? This stuff here you can deal with, right? That's not a big deal. Like, okay, a small crater. Okay, atmospheric explosion. We've had those. Okay, down here, ooh, that's rough. That's real rough, right? Okay. Has anyone ever been killed by a meteorite?
So like, wasn't there one woman who's been struck but didn't die?
That's correct. It's deeply correct. And here's her picture. It's an awesome story. Like what? Okay. Bruised their hip. Who else can say that? You got hit by something from outer space. Cut you. And then they're like taking photos of you in the, I guess maybe these are different. Anyway. So I mean, maybe more people have been hit. We don't know. But like, this is what I know about. I also went to a conference in Montevideo in Uruguay, where it was an asteroid, comets, and meteors conference. So it's about meteors, about stuff coming from the sky and hitting things. And they brought in a TV that it was in some village that like a piece of like meteor went through. So it went through their whole house, burst through their TV. They came home, they're like, what the hell happened here? There's a hole that goes straight up into space. So, I mean, they were fine, but they brought the TV. They're like, we could see which direction it came from because we can see all the things that it went through on the way in. It's pretty wild. Okay. So no one's ever been killed by a meteor. Good. But dinosaurs, no, not so good. Okay, is this a true picture? Yeah, it's a photo, right? So, photographer ran after this. So there's a number of things wrong with this. And it's not, I mean, I'm a bad artist, right? I'm not gonna claim to have any art skill, but let me just tell you what's wrong with this. One, no feathers, right? Dinosaurs probably had feathers, even if they were just decorational. In the same way that you look at like flightless birds, like emus, and they have feathers, right? Like they're not lizards. They're like the reason why we have flight. Sick. Other thing, they wouldn't turn and look. They just wouldn't. They wouldn't have time. Okay. Have you ever seen a shooting star at night? Okay. Do you ever have time to go and stare at it?
No.
No, it's like that, and you yell, and all your friends look, and they've all missed it. Right? So remember what we said. They're moving at about 30 kilometers per second. The whole atmosphere is about 200 kilometers. So it punches through the atmosphere in like less than 10 seconds. Okay? It doesn't start burning up until about 3 seconds till it hits the surface. You have about 3 seconds from when it starts being lit up to when it hits the surface. That's not a lot of time. Right? So that's two things here. What else was the third thing that I hate about this? All right, let it go. Get over it, because money. All right. Anyone ever seen this? Okay, this is the location that killed the dinosaurs. Here in the Yucatan, I'm going to show that there's a crater, massive crater called the Chicxulub crater. So here, let me just zoom in on this. Can you see it? Where is it?
Yeah.
Green. What green line? Yeah, exactly right. Exactly right. That's the crater. You can see it from space, right? Of course, they didn't kind of like space, right? Okay, so you can see it there. And another cool thing is if we fly spacecraft over it, we'll notice that this is also where the cenotes are. You guys know what cenotes are? Yeah, there's sinkholes. Okay, yeah. They're like, if you look at a map, I can overlay it, not this one, but on Tuesday, I'll show the overlaid cenote map. There's just blue dots all the way around that. It's showing you the edge of the crater. This is what it looks like when you look at how concentrated is the material. So remember we saw that there's these perfect circles, and then sometimes like the one that we saw on the moon had a little thing in the middle. This is that little thing in the middle. There's like rings to it. All right, so this is big, smashed into our planet, messed everything up. Oh, here, what are these blue dots? I forget. I'll find out. This is real data, right? And then of course they overlaid the edge of the object here. So on this side, it gets all erased with the ocean. That's a zoom in, super easy to see. Oh, these are the cenotes, right? Yeah, these are the sinkholes that the water moves. The white dots. Okay, also not a picture, right? Simulation. Probably more accurate than that other one. Okay. A couple things to note here is the relative size of the atmosphere to the planet. So if you've ever held a basketball, you imagine the Earth is the size of a basketball. Take one piece of paper and place it on top of that basketball. That's the entire thickness of the atmosphere compared to the planet. Okay? So we live in this like tiny little film on the outside of a basketball and at the bottom of that film. Okay? So this thing comes in smashes into the planet, does a lot of messed up stuff. Okay? It excavates, remember we said that it deposits energy and then it explodes. And as it does that, it launches boulders that are the size of mountains on trajectories that are going to go around the planet. They're going to fly all over the Earth. The reason that we know this is true is because there is a line that we see in the geographic record that before this, there are dinosaurs, and after this, there's no dinosaurs anywhere on the planet. And this record, this line, it's called the KPG boundary, distinguishes the two time periods in basically the fossil record. And there's something very unusual in it called iridium. It's an element that's found very commonly in space stuff, but not found on the Earth. And we find it everywhere. We find it in Colorado, we find it in Spain, basically blanketed the entire Earth. And people were like, huh, that's weird. So they knew something killed the dinosaurs, something having to do with iridium, but they couldn't necessarily find what this was until they were able to look at those mass concentrations and discover the outline of this object, right? And then they could time exactly how old it was. And they could do simulations to figure out exactly all the bad stuff this did. We got an example of this today. Everyone noticed that it's real cold, right? Okay, so what's happening there? If there's dust and haze in the atmosphere, then light doesn't make it to the surface. It doesn't warm us up, which is great for us. We're sick and tired of the triple digits, right? But that's just a little bit of a fire. Imagine if most of the world was on fire. Okay? So in addition to this happening, each one of these stuff drops, smashes into the surface, and creates secondary fires, secondary explosions. Okay? So nearby, you get tsunamis. It's really hot. If you're very close to it, instant death. And that's instant death just from the fact that the sound compresses your lungs when you die. That happens, for example, if you stand too close to a rocket launch. Yeah.
That spider circle around, is that just shock wave?
Yeah, that's supposed to be the shock wave, right? So you would imagine that it punches in and then immediately compresses the air, right? So it punches right through the atmosphere. Atmosphere doesn't notice, and it moves it out of the way. And so this thing is just moving out, killing anything, right? Just by collapsing their lungs. Yeah. It looks pretty, right? It's really violent. So this is how you get a mass extinction, right? Yeah, you punch a hole, these things become ballistic missiles and they land and they bomb the rest of the ground. So then you cool the whole planet down, you put dust everywhere for a really long time. And then all the plants, they get so finicky when they don't have sunlight. If you move it in and then it doesn't grow well. So just imagine like there's no sunlight for like 100 years, then everything would die, right? So that's the mass extinction.
Did they fashion like the bombs after this, or did that just come as like a, oh, hey, that's like that?
No, coincidence. Yeah, so the type of energies are similar, right? Like we don't have a bomb that could do that. If we blow an atomic bomb, it's like 1 pixel here, right? Like, right? The Earth is very big. This was bigger, right, than we think. And we'll talk about another big thing that hit us that still shows the memory of that. Okay, any other questions about this? I can talk about this for ages, so just stop me when you're done. Yeah. No, I think it's pretty well mixed. So I think what ends up happening is just like there wasn't large concentrations of iron and nickel in Barringer crater, what happens is you punch in and then you blow the thing up. And so it like mixes in that explosion process. Yeah.
Also be like the stuff that actually would have stayed in the crater might have melted as well.
Yeah, definitely the stuff that was in the crater gets melted, but right, it's like you can imagine the size of the crater, right? So imagine that the thing is this big. The object that hit it is this big, right? So that just punches directly through the surface and then stops when it's under the surface. And then when it stops, it rebounds and it pushes everything out, right? So it's not like the whole thing comes in and crashes into the surface and then it moves up. It goes under and then it bounces. Okay? Yeah.
I just thought about this So you said like the stuff that's like closest to the impact, like it starts like enveloping with all like the stuff that pushes out. What happens like on the opposite side of it directly?
Very good question. I was gonna show this in my other class, so on Mercury, which is I think the only example of this happening, there's a big enough impact, you smash into it, and it basically shakes the entire planet. On the other side, you get a mountain. So I was gonna do that for my other class, I'm gonna show it now in both, so you'll both see it on Tuesday. Any other questions? Okay, all right. Boring stuff, learning. Ugh. Okay, so what do craters tell us about surface ages? Okay. So if there are craters more than other locations, this tells us something really important. Let's assume that the clickers worked here. Let's try. These work. Okay. We're going to compare the number of lunar impact craters in the lunar Maria versus the lunar highlands. The lunar Maria is the dark region. The lunar highlands are the light regions. Which surface formed more recently? And I'm going to click away from this so you can see the surface, and then we're going to answer, okay? So here's the, come on now. Okay. So here's the Maria here, and here's the highlands, right? Highlands are this lighter part, and then these sections here are the Maria. Okay. The question is, compare the number of impact craters in both of them. Which surface formed more recently? Is it A, the highlands, B, Maria, C, we can't tell, because you haven't told us yet, D, they're both the same age, 4.5 billion years old. So let's vote. Let me know when you're ready. On 3, 2, 1. Okay, lots of 4s, 3s, 2s. No one likes 1. Okay, well, couple ones. Do you want to turn to a friend and ask them whether or not they got the same answer? If we have time for that. Yeah, we have time for that. We have 5 minutes. If they have the same answer, try someone else. Both have 1, just turn. Yeah. You can ask them in the front. You can ask them in the front.
Like this.
You don't know.
Can you try it now? Let's see. Okay, let's try it now. Figure it out. Click in if you have the answer. Okay. The question is, which formed most recently? About 50 respondents. Anyone else want to click in who hasn't? 53? Okay. All right, good. You want to explain their answer? Yeah.
I don't know. I said Maria.
Mhm.
The craters of the highlands, as we know, a lot of them have been that heavy bombardment period at the beginning of the solar system. But the Marea comes from volcanoes, and I feel like, since that wasn't when everything was still flying around, there's some chance that could have happened much later, whereas the highlands, kind of had that one point in time before.
Good, yeah, that's great extrapolation, right? We're using information about when the highlands formed or when that bombardment was happening at the beginning of the solar system. There's lots of material. Another thing that I might say, right, is that like the volcanism that is happening in the Marea is occurring similar to how erosion works to reform the surface, right? Like melt it away, get rid of it. So the fact that there are fewer craters here, right, indicates that if there were craters there, it must have covered them over, right? So in fact, the Marea is the younger of the two surfaces. So even though the moon itself is 4.5 billion years old, the surface itself can have different ages. So for example, Hawaii, the new one, is brand new, just came out, right? Rocks just being formed, right? As opposed to the moon, very old, but some pieces are older than the other pieces. Okay, we're almost there, don't leave yet. Oh God, that's horrifying. What happened? Oh, okay. All right, so fewer craters means a younger surface, okay? So the Earth, quite a young surface, right? That means that the surface has been repaved, right? You have like a street with a lot of potholes in it and stuff, not a new street. They fill in the potholes, new street. Good, okay. Hold on, let me show you one thing before you leave. All right, this is Mars. All I did was unwrap it, okay? So I'm gonna show you, you're gonna become experts in Mars geography. No, just kidding. Okay, this is Olympus Mons. This is the Tharsis region. So this is that region where there's a really big like volcanic plume. And then the largest canyon in the world is, in the solar system is Valles Marineris. It's here. And now I'm gonna show you the work of a grad student who went through and painstakingly found every crater that he could. Okay, ready? That's a lot, right? So let's look at the first thing that we notice. Look where the volcanoes are. Not as many craters, right? Why is that? Because the craters get melted away by the new lava. Look this region here. This is something called Hellas, this one here. That probably had a bunch of stuff in it. Boom, punch into it, delete all the old history, right? Okay, now we're gonna do one more. Which of these two is older? This one? Or this one? And what you're seeing here, each one of these blue dots is a volcano. Each one of the green dots is a volcano. I'll explain what this is in a few seconds. This one or this one? Which one's older? This one, right? Yeah, this one, the red is so red that you can't tell the difference here, right? It's like completely overrun. What is this body? Which solar system body am I showing? Venus. This is Venus. These are the craters on Venus. Okay. So this is the entire surface. I believe the blue ones, I forget exactly how this works. I'll double check this. It's like a size thing, how big the blue is versus the green. What this tells us about the age of Venus's surface is that it's not older than 600 million years old. Is that surprising? Well, let's think about it this way. There are pieces of the Earth that are several billion years old. Okay? We couldn't find one section on Venus with an age older than 600 million years old. That's roughly the age of sharks. Not like one shark, but like as a species, right? Okay. So the biggest thing that should jump to your mind is what? How? Venus is quite similar to us. You'll see the ways in which it's different. But its surface is very, very young. Okay, and that tells us a lot about why it's kind of a catastrophe to live in. Okay. Okay. If you haven't turned in your homework, please do that. If you haven't picked up homework 1, please do that here. If you haven't given me your lecture tutorial, please give me your lecture tutorial. Oh, the homework, yeah. On the home. Yeah.
Oh, I wasn't here on Tuesday.
Okay.
Like, I saw.
What's that?
I saw.
Yeah, I prefer if you could find a friend to do it with.